Ben ritrovati. In the last lecture we have reviewed the basics of a quantum theory of scattering, and in particular we have discussed the regime of S-wave scattering, that is the only relevant scattering channel for ultra-cold collisions. And in this regime the relevant quantity is the scattering length, and so we have seen that, for example, the collisional cross-section depends on the square of scattering length. And we have also seen that the sign of a scattering length is associated to the character of interactions that are repulsive for positive scattering length and attractive for negative scattering length. So in this video, we would like first to see the connection between the scattering length and the scattering potential, and then to see how the scattering length depends on the particular choice of atoms for a cold atom experiment. So let's start with a discussion of a connection between the scattering length and the potential. However, there is a problem in the sense that the real interaction potential in cold atoms is rather complicated, so it's not possible to work out an analytical calculation. So we have to consider some toy models. And so we will start from the discussion of two examples. So two simple models. First, we will consider the case of a potential barrier. Then we will consider a potential well. So let's start with the first. And so let's consider an interaction potential like this, that is a potential barrier. It is, I've called it a rectangular spherical barrier, in the sense that, of course, it is rectangular because the shape of a potential as a function of r is a rectangle, but it is spherical because this potential depends on the radial coordinate r, so it is isotropic if we consider the angular dependency of a scattering. And so this potential is zero for distances larger than b, and b will be, of course, the barrier width, and it is v0 for distances smaller than b. And then, of course, the distance cannot go negative, and so we assume that this potential goes infinitely high for r equals 0. Okay, so of course this potential is completely not realistic, because we have seen that for neutral cold atoms the potential is kind of van der Waals potential, so it looks more like a potential well, than a barrier. However, so we'll consider the case of a barrier so as a warm-up, so to understand some connection between the behavior of a wave function and scattering length, and then we'll consider the case of of a rectangular well that is much more physical. But let's start with barrier. And so we consider S-wave scattering, and so if we want to compute the scattering length, we need to evaluate the S-wave phase shift. So we need to know the wave function. So we need to go back to the framework that we have reviewed in the last lecture. In particular, we need to solve the radial wave equation. And so let me go back to what we wrote in the last video, and also I have the opportunity to correct for a mistake that I made in the last lecture. And so the mistake was indeed regarding the radial wave function that I wrote here, in the sense that when I wrote the Laplace operator in spherical coordinates, I made an error, because when you expand in spherical coordinates the Laplace operator, so in addition to the angular momentum part, so you don't have just the second derivative with respect to the distance, but you have also an additional term. So let me correct that now, and then we will go on in the solution of this equation. And so let me go back to the previous screen. Okay, so what I missed, shame on me, was this red term in the equation. So in addition to the second derivative with respect to r, you have 2 divided by r, derivative with respect to r, that basically has had no consequence until now, but now that we want to solve this equation, it is important now to consider it. And so in particular, you know that from the solution of a hydrogen atom, for example, that you write the wave function as this reduced wave function u divided by r, because if you expand the calculation and so you let operate these differential operators on u divided by r, everything is much simpler, because you end up with what we can call, in a more correct way, the radial wave equation, that is this equation. So in which you are just left with a second derivative with respect to r, and so then you have the potential v, and then you have the centrifugal term. But in our discussion today, the centrifugal term can be discarded because we are interested in S-wave scattering. So L equal to 0, so everything simplifies, and so the equation that we have to solve now is this equation, in which basically is a kind of effective one-dimensional Schrödinger equation for the function u, in which you have the second derivative of u plus the potential, and then of course this has the form of eigenvalue equation that we need to solve now. Okay, let's do that. And now we need to consider that our potential has a discontinuity for r equal b, and so we need to solve this equation in the two domains, r smaller than b and r larger than b. So let's start with r smaller than b, and so I can write this equation in this domain, minus h bar squared divided by 2 mu second derivative of the wave function, so let me indicate it with two primes, plus the potential. So the potential in this region, so for r smaller than b, let me call it region 1, is given by v0. And so we can parameterize v0 with k0, with this wave vector that I have indicated here on top. And so we can write the potential simply as plus h bar square k0 square divided 2 mu minus the energy, and also the energy can be parameterized in terms of the wave vector k. So this of course is multiplying u, and this has to be equal to 0. So we can simplify the h bars and the reduced masses, and so we find minus u second plus k0 square minus k square times u equals 0. Okay, and let me write also in the region 2 a similar equation that is now even simpler, because of course now the potential is 0, and so the equation is minus h bar squared divided by 2 mu second derivative of u minus h bar square k square divided 2 mu times u equals 0. That becomes minus u second minus k square u equals 0. And let me also recall that we are interested in solutions with positive energy. This is why I have written this energy as h bar square k square divided by 2 mu. And in particular then, since we are interested in the low energy solution, we will take the limit of k that goes to 0. But we will consider this limit only in the final solution. So let me free some space and rewrite only the equations like this. And so you see that these equations are rather simple and they have the same structure. The only difference is the sign, in the sense that this quantity is of course a positive quantity, but also this quantity is positive. And so the difference between the character of the two solutions, in region 1 and region 2, will be given by the minus or plus in front of the u term. And this, of course, comes from the from the choice of the energy that we made. So the energy of a solution that is indicated in red here above, is above the potential energy in region 2. So, I mean, in some sense, region 2 is allowed for the particle, while region 1 is forbidden because the energy now is smaller than the potential. And so let's write the two solutions, and let's start, for example, from region 2. And of course, region 2, the equation is that of a harmonic oscillator, and so the solution will be U2. We can write it as A2 sine KR plus B2 cosine of KR. Or I can write this expression, it is the sum of two sinusoidal functions, sine and cosine, as one sine only, in which I consider a parameter for the phase. So I can write it also as C2 times the sine of, let me call it, KR minus A. So where, of course, C2 and A will be functions of the other two constants, A2 and B2. And I've written this solution in this last form, and in particular I've chosen the symbol A for the quantity inside the argument of a sign, because you can now recognize that writing the solution U2, that is the solution that also holds for large distances, so it is the solution in the allowed region. So writing the solution this way, of course, makes a direct connection with the meaning of a scattering length, because if I go up and remind you the meaning of a scattering length, so we have seen that basically the scattering state at large distances can be written as a sine of k times r minus a. So that a that I have indicated now in the expression for the radial wave function in the outside region as of course, the meaning of a scattering length. So we will determine a on the basis of the parameters that describe the scattering potential. And in order to do that, we also need the solution in the forbidden region, so U1. And U1 will be given by not a sine, but a hyperbolic sine and hyperbolic cosine. So we can write it as A1 sine, hyperbolic sine of square root of k0 square minus k square times r plus the cosine, hyperbolic cosine, but now we can ask for the wave function in 0 to be 0. So we want u1 0 to be 0, and we want this because this basically corresponds to the request for the total radial wave function, that is u divided by r, to be regular for r equals 0. And so because of this requirement, so in this expression u1 we can only keep the first term, because the hyperbolic cosine is different from 0 in the origin, while the hyperbolic sine is 0, and so we are just left with a1 hyperbolic sine of square root k0 square minus k square times r. And now, of course, we need to ask for the wave function to be regular at the intersection, at the boundary between the two domains. So we ask for the continuity of both u and its derivative. And so let's write the conditions explicitly. So we want u1 evaluated in B to be equal to u2 evaluated in B. And we want u1 prime to be equal to u2 prime. So First condition is A1. Hyperbolic sine of square root of k0 square minus k square times b equal to C2 sine of k times b minus a. While the second equation gives, derivative of u1. So the derivative of a hyperbolic sine is the hyperbolic cosine. So we have a1 hyperbolic cosine of square root of k0 square minus k square times b. And then the derivative of the argument, and so this is square root of k0 square minus k square. Fine. And this has to be equal to derivative of u2. That will be, so c2 times the cos of k times b minus a, that multiplies the derivative of the argument, that is k. Okay. So we have to satisfy these two conditions, and the easiest way to work out the result is to take these two equations and divide the first by the second. And so what we get is the following. So we divide this term by this term, and we get 1 divided by square root of k0 square minus k square times the hyperbolic tangent of square root of k0 square minus k square times b equal to 1 divided by k. So we do the same for the right hand side, tangent of k b minus a. And so now you see that we are very close to the result, in the sense that this expression becomes an equation for a. So this is the solution that we want to find, and you see that we know all the other parameters, because we know b, so we're supposed to know the potential. So we know b, we know k0. What is left is k, but we know that we have to take the limit k that goes to 0, and this is easy because we can, at least at the left hand side, we can put these two terms to 0, and so we get simply hyperbolic tangent of k0b divided by k0. At the right hand side, so we have the tangent divided by k. Now we are taking the limit k that goes to 0, and of course we can approximate the tangent with its argument, and so this will be k times b minus a divided by k, and so of course k simplifies, and this becomes just b minus a. Good, and I can rewrite this last result that does not depend on k in this form. So I can write that the scattering length can be written as b times 1 minus the hyperbolic tangent of k0b divided by k0b. And so this is a simple relation that connects the scattering length to the parameters which describe the potential. And for instance, let's suppose to have a fixed width of a barrier, and let's suppose to change its height. So let's see how this scattering length depends on V0, or in other words, how it depends on K0. And we can plot this quantity, and it is rather simple. So in particular, what do we see? We see that. So let's plot A as a function of a parameter k0b. And so when k0b is equal to 0, so the barrier is infinitesimally small, the hyperbolic tangent can be approximated with k0b. So this fraction will go to 1, and so a will go to 0. And so for k0 equal to 0, we have 0 scattering length. In the other limit, so k0 that goes to infinity, the hyperbolic tangent goes to a finite value, that is 1, and so the fraction will go to 0 because k0 goes to infinity, and so a will go to b. So in the asymptotic limit of very large, very high barriers, so the scattering length will be given by b. And so in this graph, this quantity will go to 1 as asymptotic value. Something like this. So, in order to understand better what's happening here, I will show you the result of some numerical calculation, in which basically I take these equations and I've just plotted the results with Mathematica. So I plot both the scattering length and also the wave function, so for different parameters, and so we will see directly this phase shift that appears when you have a non-zero scattering potential, and we have a very clear understanding of interpretation, of a geometrical interpretation of scattering length. So let me take the Mathematica file. That's it. And these are basically the same equations that were on the whiteboard before. And so we have the parameter a with a solution that we have given. So we have the two expressions, one for the wave function, one is the sine, one is the hyperbolic sine. And then we have the equation and the condition of continuity of the wave function for r equal b. And so I can give you a visualization of the solutions in the following way. So what will you see here? So on the plot on the left, so you have the wave function, and so in particular, so you will see both the scattering state, so the solution for the scattering problem, and also the incoming wave, so the solution to the Schrödinger problem without scattering, so that I will call free solution. And so in this case, we don't have any barrier yet, so these two solutions are overlapping. So the gray region is a kind of forbidden region because this is for r, negative r, and so the solution is defined only for positive distances. And okay, and so in this plot you will see both the wave function and the energy of the barrier that will start to grow. And for the wave function, I've considered a non-zero momentum, just to have a visualization of what happens. That is, however, small compared to the values for k0. And then on the small plot, you will see instead the scattering length. And so let me show you now an animation with the same results that you have derived on the whiteboard. So you see that as the potential barrier that is indicated in red in the plot on the left, so this potential barrier is growing in size, you see that the scattering state is displaced more and more towards positive distances. So you have a delay of the scattered wave function. So this is the case of a positive scattering length. And so the scattering length is the red point that you see in the plot on the left. And this red point is the intersection of the extension of the scattering state, that is the dashed line, with the axis. So it is the distance from the origin at which the extension of the scattering state becomes zero. And so you see here that when the barrier is very large, so the scattering state has a node in correspondence to B, so the actual scattering state vanishes in B, and so the scattering length becomes equal to the width of the barrier. In the case instead of small barriers, so you see that the wave function penetrates a little bit inside the barrier, so you have this exponential penetration inside the forbidden region, and so in this case the extension of the wave function is deviating from the actual scattering state, and so the red point marks the intersection of a dashed line with the axis. So here the scattering energy is very small, and so you can see this dashed line, red line that is almost zero. So this is the energy of a scattering state. So we are really considering the very low energy limit of a scattering. And in the plot on the right, you see the same plot that I have drawn on the whiteboard before. So the scattering length is a function of k0b. And so you see this function that starts from 0. And of course, it has to start from 0, because if you don't have any barrier, so the scattering state is the free solution. And instead, in the case of very large barriers, so the scattering length corresponds to the size of the barrier. So in some sense, so this is the limit of an infinitely high barrier. And so this restricts the space that is available to the wave function. So in some sense, this scattering potential becomes a hard wall. So in this hard sphere limit, so the scattering length basically reduces to the width of a barrier. Okay, of course, here the interaction is always repulsive, in the sense that the scattering length is always positive. And of course, this has a quite clear understanding also from a classical point of view, because you have a positive potential energy. So atoms will have to pay some energy cost if they want to stay close one to each other. And of course, this means that the collision will have a repulsive effect. And a much less intuitive result, especially if considered from a classical perspective, will be already given by the next example, so that of the potential well, that is more interesting and also more related to the real interaction potential that we have between atoms, that has some attractive part and then a repulsive core at 0 distance. And so let's consider this case. And this is the potential well. So you see that also in this case we have a very simple potential. So it is a rectangular potential in which the potential is 0 for distances larger than b. That will be again the radius of our well. And instead it is minus v0 for distances less than b. And so, of course, just a change in the sign of the potential, but this change in the sign will lead to completely different physics. And so you see that this potential is already something that is closer to the actual interaction potential between atoms, because it's not the van der Waals potential that I was sketching to you in the previous lecture, but you can see that is a kind of first approximation to it. In the sense that there is some potential well, and so atoms cannot, of course, go to negative distances, and then at some point, for distances larger than b, so the potential basically does not change. So this is a kind of a good approximation to a short-range potential. Okay, and so I kept all the calculations that we made before. So these are the same calculations that we have already done, just because you will see in a moment we need to change here and there some little things, and so we will arrive to a result that will be very similar but also very different. And so let's follow from the start. And so what we have to do is to change basically the signs of the equations in region 1. So this is the only difference. So in region 2, everything will be the same, because the potential was 0 also in the first case. Now the sign in equation 1 has to be changed, and so in particular region 1 that was forbidden before, now it becomes energetically allowed region. And so in particular, equation 1 should be modified in this way. So I have to put a plus here and a plus here. So basically you see that in analogy with region 2, in region 2 you have this k square that comes from this energy here. And instead now we have k0 square plus k square, that is this energy with a sum of the energy of a potential well. And so they are both positive quantities, and so you have k0 square plus k square. And so it follows immediately from the previous approach. Okay, and so we have to change the solution for region 1, and instead now of the hyperbolic sign solution, we have a normal sign solution as you have for region 2. And so now we have to write here the normal sign. So please follow me as I update the equations of the square root of k0 square plus k square. So this is the updated solution for region 1. And then we need to change the continuity equations, and in particular the two expressions at the left-hand side. So in the first equation we have just the sign, again, of square root of k0 square plus k square. On the right-hand side, nothing changes. And on the second equation, we have, again, the normal cosine, and I have to put the sign plus inside the square root. When I divide the first by the second equation, I get 1 divided square root of k0 square plus k square times the normal tangent of square root of the sum of the two contributions. Everything is the same on the right hand side, and so in the last passage I can now, as before, I can take the limit of k that goes to 0, so these two k's will be discarded, and so we have just the normal tangent of k0b. And so in the final solution, everything is the same except the hyperbolic tangent that becomes a simple tangent. That's all. So this is the result for the rectangular well. So you see that the formula is very similar, but the result is very different. And so let's plot this quantity as a function of k0b, and then I will show you again with Mathematica the animation with result. So now, what do we have? Again, a graph of A divided by B as a function of k0b. As before, when k0 goes to 0, this expression has a limiting value of 0. So no well, no scattering, and no scattering length. Then this expression goes down, and this comes from the fact that the tangent grows faster than its argument. So remember what is the plot of a tangent function. Tan of x has a behavior like this, you know. So it starts linearly, and so, but then after this linear region, it grows faster than its argument. So this quantity will be a number higher than 1, and so the scattering length will be negative this time. And this makes sense because we have now a potential well instead of a barrier, and so it makes sense that atoms are attracted, and so the scattering length is negative. But then at some point you realize that the tangent is a very different beast, and so differently from the hyperbolic tangent, so the simple ordinary tangent has poles. It goes to infinity, and then it starts again from negative infinity. And so something interesting should happen, of course, in correspondence of these poles. So when K0b is equal to pi half, the scattering length will go to minus infinity, because we have a minus sign here. And then after, for values larger than pi half, so the tangent starts again from minus infinity, so this means that the scattering length should start decreasing from infinity. And then if we plot this function, we realize that this is something like this. So we have many poles that are the first for pi half, the second for 3/2 pi, then 5/2 pi, and so on. So we will have a divergence in the scattering length that will change from negative to positive each time that K0b is an integer n plus 1/2 times pi. So this is a very different behavior from what we have seen before. This simple potential well does not give a unique sign for the scattering length. So depending on the value of the depth of this well, you can have a scattering length that is negative, then positive, then negative, then positive, as this potential well becomes deeper and deeper. So what the hell is this? So why do we have this scattering length that changes sign at these values, these particular values of a potential well depth? So in some sense, there should be some resonant process here. There should be a resonance in correspondence of which, and this K0b equal to n plus 1/2 pi is the resonant condition that corresponds to this process. So there should be some, some enhancement of scattering length. And this is a kind of strange enhancement because this comes from infinitely attractive on one side to infinitely repulsive on the other side. So, before looking at what happens with Mathematica, let's think to what is different from the potential barrier to the potential well. So it seems that the problem is rather similar, so the potential looks similar in the two cases, only a sign is different. Why should we have this resonant behavior? So there is one important difference between the two potentials, actually. And this difference is in the fact that a potential well can support bound states. So negative energy solutions that are not the solutions that we're interested in, but solutions at negative energy that correspond to a wave function that is localized in the potential well. Of course, the potential barrier does not have bound states. And so the physics of these bound states is extremely important to explain the behavior of a scattering length that we have seen. In particular, I will demonstrate for you that this resonance condition that we have highlighted here in the yellow box corresponds to the situation for which this potential well supports a bound state with energy, with binding energy that is close to zero. In other terms, a bound state whose energy is very close to the energy of a scattering state that also will be approximately zero in the low energy limit. And so we will have a resonance condition. So in some sense, the presence of a bound states will enhance the effect of a scattering. So let's go step by step. First, let me demonstrate that this condition corresponds to having a bound state at energy that is approaching zero. And the calculation of the bound state energies is actually quite simple because also in this case I can reuse all the equations that we have written before. And also in this case I will just make a few modifications, and in particular with respect to the previous case of the scattering state, of a scattering solution for the potential well, in which the energy of a solution was positive, the only difference is that now we are looking for negative energy solutions. And so I can rewrite the same equations, but the only difference now will be a sign minus to the energy. And so this means that let's start with region 1. In region 1, we will have k0 square minus k square, because the energy will be negative now, and so in some sense this is a kind of reduced potential well, not k0 square, but k0 square minus the energy that is k square. So we are subtracting this energy to the potential well depth. And then in region 2, we have something different now, because region 2 now becomes a forbidden region. So we have a sign minus here. And so this will mean that while for region 1 the character of a solution will be still oscillating, although with a minus sign inside the square root here, for region 2 we have something different. So we have again hyperbolic sine and hyperbolic cosine. Or we can take into account now an obvious boundary condition, that is our requirement of a wave function to go to zero at large distances, because we want this wave function to be properly normalized, and so of course we want u2 to go to zero when r goes to infinity. And since hyperbolic sine and hyperbolic cosine are just combination of an exponential with positive or negative argument, of course only the negative argument is admitted. So we cannot have a d2 contribution with e to the plus kr, because this will diverge at large distances, so we should have d2 equals 0. And so we have an exponentially decaying wave function outside the allowed region. As before, let's consider the connection of the two solutions at r equal b. And now, on the left-hand side, I will just put a sign minus here. And I should instead change expression on the right-hand side. So let's see what do we have. So the u2 for r equal b will be given by c2 e to the minus kb, and the derivative u2 prime will be derivative of exponential is the exponential itself times minus k, that is derivative of the argument. And so we will have minus c2 k e to the minus kb. So we make the ratio of the two expressions. So on the left-hand side, so we have, again, the sign minus here. At the right-hand side, we have a very simple expression, because we have just minus 1 over k. So this equation will admit a discrete set of solutions that will be the bound states for our potential well. But now we are interested in finding the values of the potential well depth, for which we have a bound state energy that goes to 0. So we are interested in looking at the solutions of this equation for k that goes to 0. So we want to find a bound state that is very, very, very weakly bound. So with a binding energy that is approximately 0. And so what do we have? Actually, this is very simple, because now On the left, again, we can neglect k with respect to k0, and so we will have tangent of k0b divided by k0, and this quantity, as k goes to 0, should go to infinity. And of course, when does this happen? So when the tangent diverges, and so when k0b is equal to n plus 1/2 times pi. So when this condition is met, this means that we have a bound state of our potential well at energies, negative energies that are close to 0. And so you see that this happens exactly for the same condition that we demonstrated for the divergence of a scattering length. So the scattering length diverges every time we have a bound state that has an energy close to 0. So an energy that is close to the energy of a scattering state. So let's see all of these with Mathematica. And so we will have a clear now understanding of the reason of this resonance behavior. And I will show you now the same animation, but now for the potential well. So you see that at the beginning, so the scattering length becomes negative, but rather soon you have this behavior. So as the potential well increases in depth, you see that you have these bound states which are appearing. So you see here quite clearly that these lines are the bound states that we have derived in the previous calculation, and you might see that as soon as a new bound state appears, so you have this resonant enhancement of a scattering. So there are a set of things here to be discussed. So of course, this is a finite potential well, so it has a finite number of bound states, contrarily to what happens for the infinite well. And so they can be counted, and so you see that each divergence corresponds to a new bound state entering, in some sense, the potential well as the depth is decreased. And you see quite clearly from the scattering state inside the red region that it is an oscillating function. And so you see that the number of oscillations, so the number of nodes of a wave function inside the red region increases when the depth of a well is increased. And so in some sense, the wave function inside the red region reflects the wave function of a bound state. So you know from the square well that the higher is the energy of a state, the higher the number of nodes of the wave function. So you can see it quite clearly here. And so this resonance condition corresponds, of course, to the best matching conditions between the wave function inside and outside the red region. And this also corresponds, of course, to the fact that the two solutions, so the scattering state and the bound state, will have more or less the same energy that is close to 0. So you have this strong resonance enhancement of the scattering when you have a bound state with almost 0 energy. And there are some aspects of this behavior for which you can have a direct explanation, even in classical or quasi-classical terms. For example, the idea of this resonance. So in the case of a potential barrier, there was no state available inside the barrier. And so, we didn't have any kind of physics like this. But here you have some discrete values of energy for which you can form a bound state. A bound state is a kind of, you can think to a molecule, because this is a bound state for the R variable. So the R variable describes the distance between the two atoms. And so a bound state of this interaction potential means a molecule, so a state in which the two particles remain confined. And so if the energy of this state matches or quasi-matches the energy of the atoms that are colliding, it makes sense to to realize that that effect of the atom-atom interaction, so the effect on the scattering should be enhanced. So you might think in some sense that you have these two atoms that are colliding, so they come close one to each other, and so when they're close, so their energy is almost the energy that is good for them to form a molecule. So they think if should we form a molecule or not, but then they remember that they have positive energy, and so they go away. But in some sense, they keep memory of their encounter. So it's kind of almost marriage. And so, of course, this is a very romantic explanation of what happens. So I'm not using words that are good for physics, but I mean, in some sense, this is what happens. And so you see it from the wave function, because the wave function, when you have this resonance, becomes amplified in the central region. So you have this resonant enhancement of the probability of being in the red region. But then you have also some kind of non-immediate, less classical effects. For example, already something that is quite difficult to be understood, for which you lack some kind of physical explanation, is why this interaction will become repulsive. Because one could think naively that, yes, the scattering cross-section can be amplified when the two atoms come close together and their energy is quasi-resonant with a bound state, but then why should I have a positive scattering length? And so this is already something that is more difficult to be explained, but we can invoke an effect of quantum mechanics that you can see here very clearly, that is called the quantum reflection. What is quantum reflection? So in quantum mechanics, if you consider a potential well, so the potential well gives you a probability of reflection as in the case of a potential barrier. And in particular, when this potential well becomes very deep, so basically your wave function cannot enter the well. So this is what we call a quantum reflection. So a well can reflect a wave in the same way that a potential barrier can. And so we see it very clearly, because I can show you that if I go to very large K, so you see that basically here, for example, let's consider what happens here. So the penetration of a wave function in the allowed region is very small. So this situation is not so different from what happened in the potential barrier case. So in the potential barrier case, so basically you had the same. So when the potential barrier is very large, so you have a node of a wave function for R equal B, and the wave function does not enter the red region. And the same happens here. So this is a very quantum mechanical effect. So if the potential well becomes infinitely deep, the wave function does not enter at all. So it will be completely reflected by the edge of this barrier. So basically in quantum mechanics, all discontinuity in the potential will produce a quantum reflection, even if this potential is attractive. And this is what you see here, unless you match the condition for having a resonance. And so in that case, the wave function can penetrate. And so we are looking at this very nice physics. And so when you have this condition, you see that the scattering length becomes very large. For example, here. And this happens because, mathematically speaking, and because you have to satisfy this matching condition on the wave function and on the derivative, and this is what comes out from the calculation. So not everything can be explained in with hands, with simple arguments, but this problem has a lot of interest in physics. And so because of this quantum reflection, you see also this apparent apparently counterintuitive result, and look now at the plot on the right with a scattering length. And so you see that especially when K0 becomes large, so basically the scattering length becomes almost always positive. So these regions that are highlighted in pink here are the regions for which the scattering length is positive. So it becomes negative only for a very, very, very tiny region around these divergences. So I spent a lot of time on this example, and this because the physics of bound states is very important. Also for many experiments and many applications, for example, regarding the formation of molecules out of cold atoms that we will discuss at some point, but also because they serve as an introduction for the last topic of the quantum theory of scattering. That is something that is new, and I think you have not studied in other courses, that has the name of Feshbach resonance. That is a very powerful instrument that we have in cold atoms physics. And the physics of bound states that we are looking here will become very important. So this is why I'm spending a lot of time on this example. And so I can conclude this part by showing to you in the same slide the result for the potential well and for the potential barrier. And I'm showing again the same results here for the potential barrier and for the potential well. And in particular, as the movie goes on, you have the same height of the optical barrier than depth of the well. So the two energies are changing with the same values, and you see here the physics of bound states that completely changes the scenario. Speaking of bound states, the last picture I'd like to show you is again this picture of the scattering length for the potential well, but now I've plotted in the lower part of the plot the energies of a bound state. And so you see here that, how should I read this graph? So you see here that you have, for example, for some specific potential depth, you have a certain number of bound states. In this case, for example, for this potential depth, you have 1, 2, 3, 4 bound states. So as the depth of a well is made bigger, so when a new bound state enters the well, so you see quite clearly here that these conditions of energy of a bound states equal to 0 really corresponds to the divergence in the scattering length. Again, same physics, but with a nice graphical visualization. Okay, that's all for now. In the next video, we will see that the physics that we have studied today for a simple choice of interaction potential can be observed even in the real world, and will help us in understanding the range of variation of scattering lengths that we can measure in real atom-atom scattering. So, thank you for watching. Take care.